In this video, we're going to talk about how we can conduct linear regressions with multiple explanatory variables. So far, we've looked at creating linear models that have a single explanatory variable as well as one response variable. In these cases, we can nicely visualize the graph like you see here because we only have two variables, which makes it easy to plot in 2 dimensions. But what if we have more than one explanatory variable in a single model? Turns out the math behind this is not particularly tricky. In a single explanatory variable model, like we see in this top equation, we have one slope, which we've designated m here, corresponding to that explanatory variable x. If we wish to have multiple explanatory variables, then what we like to do is to indicate each one with a subscript. So here we have x1 and x2. And then each one of those gets its own slope. So we have slope m1 corresponding to explanatory variable x1, and similarly slope m2 corresponding to explanatory variable x2. In both cases, we only have one intercept. And also in both cases, we only have one response variable. Now, can we visualize a multiple linear regression? Well, kind of, if we only have two explanatory variables. In this case, each explanatory variable gets its own axis in the graph, and the response variable also gets an axis in the graph, which means we can have a 3-dimensional plot, which we can just about visualize like you see here, which shows that the surface of the linear model, instead of being a line, is now a flat plane, kind of like a flat sheet of paper going through the points. However, if we had more than two explanatory variables, we'd be in trouble because we'd then need to create a 4-dimensional graph or a higher dimensional graph, and that is really beyond our ability to plot either on a computer screen or even really imagine within our minds. So to create a linear model with multiple explanatory variables, we use the LM function pretty much as we've done for simple linear models. But we add in the explanatory variables on the right-hand side of the tilde symbol. And we add them to the model with plus symbols. So here we've got explanatory 1 plus explanatory 2 plus explanatory 3. We can keep on adding as many explanatory variables as we wish to include in this way. As before, the output of the LM function is a list that contains information about the model that function has fit to the data. So if you were just to print out the output of the LM function, which we've saved in this variable model underscore MLR, it would print out the coefficients. So we can see that we have the value of the intercept that the LM function has found, and we also have a slope for each one of the explanatory variables. Each of these represents how we would expect our predicted value of the response to change if we were to increase one of those explanatory variables by 1 unit if the other explanatory variables were held constant.